Hello everybody, welcome to my TikTok video presentation. I welcome you all people to my TikTok video presentation. My name is Pranav Teja Nagula. Um, my roll number is 2195186688 and I am from CSM branch B section. This TikTok presentation is for from the subject chemistry, and I have taken the topic called high electron affinity polymers for LEDs. This is the topic that I selected, got a good amount of information. Now let's get started. Here we'll go to next slide. So, device physics and materials science of polymer LEDs. A schematic diagram of a polymer LED is shown in figure. Over here in this slide, you can see this picture here. A polymer lead can be divided into three different components. Anode, the whole supplier made of metal of high working function. Examples of the common anode are indium tin oxide, gold, etc. The anode is usually transparent so that light can be emitted through. Cathode, the electron supplier, made of metal of low working function. Examples of the common cathode are aluminum or calcium. Polymer, made of conjugated polymer film with thickness of 100 nanometer. This is a schematic setup of polymer LED. Move on to the next slide. When a polymer LED is under a direct current DC bias, holes are injected from the anode ITO and electrons are injected from the cathode aluminum. Under the influences of the electrical field, the electrons and holes will migrate towards each other. When they recombine in the conjugated polymer layer, a bound excited states, excitons will be formed. Some of the excitons singlets then decays in the conjugated polymer layer to emit light through the transparent substrates glass. The emission color will be dependent on the energy gap of the polymers. There is energy gap in a conjugated polymer because the pi electrons are not completely delocalized over the entire polymer chain. Instead, instead, there are alternate regions in the polymer chain that has higher electron density. Figure A. The chain length of this region is about 15 to 20 multiple bonds. The emission color can be controlled by tuning this energy band gap. It shows that band alternation limits the extent of delocalization. Table summarizes the structure and emission color of some common conjugated polymers. Here these two figures alternation of bond lengths along a conjugated polymer chain. A results in the material with properties of a large bandgap semiconductor B, where Cb is the conductive bandgap and Vb is the valence band and Eg is the band gap. These are the table of polymers and their chemical names and structures, and the pi star energy gap in electron volts and their respective emission peak in nanometers. These are the type of polymers that are used to make LEDs function way more efficiently according to their properties. Efficiency for an LED for any LED is defined N external is equals to N ESC star N int, where Next is the external quantum efficiency, Nint is the internal efficiency, represent the fraction of injected carrier, usually electron, that is converted to photon, and Nesc is the escape efficiency, represent fraction of photons that can reach to the outside. The most common way to improve the internal efficiency is to balance the number of electrons and holes which arrives at the polymer layer. Originally, there are more holes than electrons that arrive of the polymer layer because conjugated polymers have a higher electron affinity. and as a consequence will favor the transport of hole than electron. There are two ways to maintain the balance: match the work function of electrode with the electron affinity and ionization potential of the polymer. Tune the polymer's electron affinity and ionization potential to match the work function of the electrode. The escape efficiency is also important because a polymer lead is made up of layers of materials that have different refractive index, and some of the photon generated from the excitation may be reflected at the boundary and trapped inside the device. Improvement in internal quantum efficiency using low working function cathode. Conjugated polymer is electron-rich. The mobility for hole is higher than electron and more holes will arrive in the polymer layer than electrons. One way to increase the population of the electron is to use a lower working function metal as cathode. Braun and Heeger have replaced the aluminum cathode with calcium, results in improved internal efficiency by a factor of 10 to 0.1%. This approach is direct and fast, but low working function electrode like calcium will be oxidized easily and shorten the device's life. Improvement in internal quantum efficiency using multiple polymer layers. A layer of poly 2,5-dihexiloxycyanoterephthalidine (CN-PPV) is coated on top of PPV to improve the transport recombination of electron and holes. This is the figure 3 structure of CN-PPV. This second figure is a schematic representation of a CN-PPV and PPV uh, layer lead. The nitrile group in the CN-PPV has two effects on the polymer. It increases the electron affinity so electrons can travel more efficient from the aluminum to the polymer layer, and metal of relative high working function like aluminum and gold can now be used as cathode instead of calcium. It increases the binding energy of the occupied pi and unoccupied pi star state but maintain a similar pi to pi star gap. So when the PPV and CN-PPV is placed together, holes and electron will be confined at the heterojunction. The resulting energy levels are shown in figure. This is the figure. The absolute energies of levels are not known accurately, but the diagram shows the relative position of the HOMO and LUMO levels in the polymers and the Fermi levels of the various possible metal contacts. The differences in electron affinity delta EA and ionization potential delta IP between PPV and CN-PPV are also shown. At the polymer's interface, there is a sizable offset in the energies of HOMO and LUMO of PPV and CN-PPV. The holes transported from the ITO and electrons transport from the aluminum will be confined in the heterojunction. The local charge density will be sufficiently high to ensure the holes and electrons will pass within a collision capture radius. This setup increases the chance for electrons to combine with holes to form an excision. In addition, the emission will be close to the junction, far away from the electrode junction, which will quench the singlet excision. The result is that a multi-layers lead has an internal quantum efficiency of 10% and internal quantum efficiency for light emitted in forward direction of 25%. Based on this approach, a couple of polymers have been developed or modified to produce the desirable emission color and processing property. The drawback of this method is that desirable properties may not be complementary to each other. For example, in MEH-PPV, an alkoxy side group RO is introduced to PPV so that it can be dissolved in organic solvent, but the undesirable effect is that MEH-PPV is less thermally stable. Moreover, in multiple layers LEDs, different polymer layers have different refractive indices and fraction of photons will undergo total internal reflection at the refractive boundaries and cannot escape as light. This problem can be overcome by Fabry-Pert microcavity structure. The improvement in external quantum efficiency by using microcavity. Fabry-Pert resonance structures are also used in inorganic lead and are based on Fermi's golden rule, where M the matrix element of the perturbation between final and initial states depends on the nature of the material, and R V can be altered by changing the density of various density states. Example, using a luminescent thin films to select a certain value of V. In building a microcavity for a polymer LED, the polymer is placed between two mirrors, in which one of the mirrors is made up of aluminum. The other mirror, a Bragg mirror, is formed by epitaxial multilayer stacks of SiX, Ny, and SiO2. This is a schematic set of microcavity. Improvement in internal quantum efficiency. Doping of polymer. Doping is a process that creates carrier by purposely introducing impurities and is a very popular method in the semiconductor industry. However, this technique was not used in polymer lead until 1995 when a copolymer polystyrene poly-3-hexylethene (PsP3HT) was doped with FeCl3. Doping of MEH-PPV with iodine has improved the efficiency by 200%, and the polymer lead can be operated under both forward and reverse bias. The doping is accomplished by mixing 1 weight% MEH-PPV with 0.28% I2. The molar ratio of MEH-PPV to I2 is 5:1. This is a huge doping ratio when you compare the doping concentration of the semiconductor. Polymer LEDs on silicon substrate, an application advantage over inorganic LEDs. In the initial research, polymer LEDs were in direct competition with the inorganic LEDs and tried to achieve the existing LED standard. This is a difficult task as polymer LEDs have a lower long-term stability. However, there are some applications in which polymer LEDs have a clear advantage over the more traditional inorganic analogs. One of these is to incorporate LEDs with the silicon integrated circuits for inter-chip communication. It is difficult to build inorganic LEDs on a silicon substrate because of the thermal stress developing between the inorganic LED, usually a 3-5 based device, and the silicon interface. But polymer LEDs offer a solution. Since polymers can be easily spin coated on the silicon, the operating voltage of polymer LEDs is less than 4 volts, and the turn-on voltage can be as low as 2 volts. Together with a switching time of less than 50 nS make polymer LEDs a perfect candidate. Reliability and degradation of polymer LEDs. Now, in terms of the efficiency, color selection, and driving voltage, polymer LEDs have attained adequate level for commercialization. However, the device lifetime is still far from satisfactory. Research into understanding the reliability and degradation mechanisms of polymer LEDs have generally been divided into two areas: photodegradation of polymer, interface degradation. Polymer photodegradation. Photoluminescence (PL) studies of the photooxidation of PPV have been undertaken, since it is believed that EL is closely related with PL. It was found that there is a rapid decay in emission when PPV is exposed to oxygen. Using time-resolved FTIR spectroscopy and increasing the carbonyl signal and decreasing CC signal with time, it was suggested that the carbonyl group has a strong electron affinity level to charge transfer between molecule segments in the polymer, thereby dissociating the excision and quenching the PL. This is the figure: polymer photodegradation, change in absorbance at units versus frequency. Similar research was performed by Comston and Jensen using BCHA-PPV and P3OT and exposing them to dry air in UV irradiation. In BCHA-PPV, there is an increase in carbonyl signal with time, while the P3OT remain intact. A mechanism proposed for the degradation of BCHA-PPV involves the transfer of energy from the excited triplet state of the PPV to oxygen to from singlet oxygen, which attack the vinyl double bond in the PPV backbone, and P3OT does not has vinyl bond, so it can resist the oxidation. This figure shows the structure of BCHA-PPV and P3OT. The research described above was all performed on polymer thin films deposited on an inert surface. The presence of cathode and anode may also affect the oxidation mechanism. Scott et al. Have taken IR spectra from a MEH-PPV lead in the absence of oxygen. They obtained similar result as in Yan et al. However, a decrease in ITO's oxygen signal was noticed, suggesting that the ITO anode acts like an oxygen reservoir and supplies the oxygen for the degradation process. Polymer-led interface degradation. There are few interface degradation studies in polymer leads. One of them by Scott et al. Took a CM image of the cathode from a failed polymer lead. The polymer lead used ITO as the anode, MEHPPV as the polymer layer, and an aluminum calcium alloy as cathode. SEM images showed craters formed in the cathode. The craters are formed when the cathode metal is melted and pulled away from the polymer layer. It was suggested that a high current density will generate heat and result in local hotspot. The temperature in the hotspot is high enough to melt the cathode, and when it melts, it will pull away from the polymer. This process will decrease the effective cathode area and reduce the luminescence gradually. So this is the end of the presentation. People, I think this is pretty clear. My presentation video is clear to you all. I hope you guys enjoyed this, and for uh, thank you all for giving me this opportunity to present you this perfect tech talk video for my topic called high electron affinity for high electron affinity polymers for LEDs. And thank you for giving me this opportunity. I thank you, chemistry ma'am, and I thank you all people. Thank you.